Welcome to this course on neural shading. Thanks for watching this course today. We have an exciting 3 hours planned talking about this new world of neural shading and why it might be useful for your work. But before we get into any technical details, let's establish some background for this course. So the reason why you're watching this course is most likely because you're interested in graphics and in rendering. And so one of the things that we really care about is creating high fidelity images of 3D worlds. And for some of us, we need to get this done in 16 milliseconds per frame, or maybe 33, it depends who you ask. And this goal has driven over 40 years of innovation in graphics, in the algorithms that we use for rendering, the way that we offer and represent 3D content, and not least the hardware that ends up running all of it. And today, the amount of detail that you can put on screen in real time is something I think is really staggering. This is a screen grab of the real-time demo Aaron showed in his special address at SIGGRAPH. And this is sort of a stand-in for all the really incredible work that is shipping today that all of you are doing. But even though this frame looks good, you'd be very right to think that we're still far from done. Now, strawberry rendering might not be at the top of your list of things that you care about, but really I could have used a photo of anything, right? Because the complexity of the things around us that we casually witness every day is really staggering, both in terms of the resolution of the detail that you can see, down to the individual hairs on the berry, and in terms of the complexity of how light interacts with it. Right, the materials, the subsurface, the caustics. Once you get down to it, there's so much more going on around us than we usually model. And it's not that we can't do it. You could probably recreate this scene in 3D pretty close. You could probably even run it in real time. It's just that we can't do it at scale. We want this strawberry level of detail at the scale of entire levels or worlds. And even if you had an army of artists to make all that content, how are you going to store it? How are you going to ship it? That's a lot of data. And how in the world would you render it, especially in real time? Now, ray tracing has come a long way. If you crunch the numbers on how long it takes to get a path-traced frame at the same quality, you can get it today about 10,000 times faster than you could 10 years ago. This sounds like an incredibly large number, but really it's a combination of a few different things, one of them being the hardware itself getting faster, some of that is DLSS, and some of that is the rendering algorithms itself getting better, so that each ray that you shoot is sort of worth more. So now today we're at this point where we can render scenes like this, path-traced in real time. But what you don't want is to have to bet on another 10,000x speed up happening before you can render, the sort of level of detail that you see in the world around you. The problem with that is, in part, what fueled this curve going up, this growth in graphics fidelity, is Moore's law. The hardware got faster every year, sort of on a reliable schedule, and the graphics pipelines could evolve to take advantage of it. Today, Moore's law is effectively dead, and the hardware just doesn't get faster at nearly the same rate anymore. And so we need a new angle to approach this problem, so we can still sort of squeeze more juice out of this orange. And this is why we're talking about neural shading. So what is it? What is neural shading? What's a neural shader? Well, from the first word, you might be able to guess that neural networks are involved. And this is usually the case, but we're bending the terminology a little bit and include any part of your render that is trainable, even when it's not neural. As we'll see later, having shaders that you can optimize is useful all by itself, even when they're not neural. Second, these are shaders. They're not a separate CUDA pass that comes after your render, after you're done rendering your frame. These run inside of the rendering pipeline. And they're not, a separate special pass. They're part of your normal shaders. You can use this inside a compute pass or in ray tracing. And, how will this help with our problem? Well, you might already know this, but consumer GPUs today ship with neural network accelerators. So right now, these sit at 0% utilization while you render. And if they're lucky, they might get kicked on if you use DLSS later after you're done rendering. But this is a considerable pool of flops that you're not using right now. It's untapped compute that's just sitting there. And as it turns out, neural networks are very friendly to hardware acceleration. These are some of the more efficient flops that you can get your hands on. And this is important because when the hardware doesn't get faster each year, sort of magically, you have to start using it more efficiently. And this is one way to do it. Up until recently, this hardware was not straightforward to access in a graphics context. But as of earlier this year, you can now use them cross-platform in Vulkan NDX via cooperative shaders. However, even if it wasn't for this hardware lottery, and even if you didn't use neural networks, trainable shaders are a very powerful tool in their own right. Once you no longer have to come up with an exact solution to a problem, but you can instead solve it with optimization, you can make headway all across the rendering pipeline, from compression to materials, geometry, radiance caching, path guiding, and more. You might be able to get out more perf, higher fidelity, or sometimes even both. And this is really why neural shading can help us get to strawberry levels of detail. On the one hand, by making the components of our render more capable, by making them trainable, we need less raw compute to get there, and by making the workload itself more amenable to acceleration, we'll get more compute throughput out of our machines. So these are the main takeaways before we get into the next section. These neural shaders are a really useful new tool to have in your toolbox. They can breathe new life into old problems that might have been very difficult to solve before. And you might be able to do so at really high performance. And this is really not about catching the buzz around AI or anything like this, but this is about a useful tool that's practical today. Now, of course, this is not going to make magically everything better. Problems that you are already solving well or for which you know an exact solution are not going to automatically improve if you throw a neural net at it. And you need to think carefully about where they might be useful. And much like any new thing in graphics, you'll need new tools, new programming models, and new algorithms. And you might need to acquire some new skills and do clever engineering to make full use of them. And so to help you get started with that is exactly what this course is about. Some of these concepts might be foreign if you haven't done optimization before, and we designed it so you don't need any pre-existing knowledge. Regardless of your skill level, though, you might pick up some useful tricks along the way.